Hello, hello, hello. Welcome back, guys. It is Saturday, the 30th of May, and today we are doing astrophysics. I say we. We're going to be doing some of astrophysics. I really doubt there's time to cover like all of astrophysics, especially because apparently there's like some sort of football match on today or whatever, and I just like fully didn't know. Had like a student, my last guy, I had it too. He was like, "Are you watching the match?" I'm like, "What match?" And then they hit these sort of like when it's on at 5, right? I'm like, oh, should I move the stream earlier? Is this going to cause a problem? And then I went, no, because this is a community of physics nerds, and I think the Venn diagram does not have a very significant overlap of people who are very very committed to watching the game. That said, I know it's very like it's not a sport I grew up with. It's not a sport I have any interest in. And then I like moved to the UK, and then everyone was like obsessed with it, and then I was like, no. But I do know that people are like really, really territorial. So if you're like a big Arsenal fan and it's like, no, this is high holiday even, then feel free to dip. But I imagine, like, stereotypically speaking, I imagine there's not a huge overlap in our audiences. So I think we should be fine. Yeah, I hope you guys also enjoyed the heat because it has been so hot, like outrageously hot. And today's the last day of it. And I actually think it's kind of a good thing because, like, yeah, you can get a bit of a revision break. You can go outside and enjoy the sun, but also it means you're not like deathly hot in the middle of your exam hall. Like a lot of schools don't have great AC when it comes to exam halls, and so the fact that it's dipping down again, yeah, it's just been bad. You really like physiologically cannot think at your best when you're like overheated like that. So I'm really glad that, especially because this week is a big week coming up. There's a lot coming up this week. You've got your Phys 2 for everyone on Monday. I'm looking at my calendar. We've got lots of GCSEs happening this week. We've got A-level math happening on Wednesday. There's some chem happening on Tuesday. There's further stuff for the mech happening on Friday. Like, it's just a big week. So the fact that the temperature is going to calm down a little bit, I think is kind of good. Because yeah, you can't think, you can't sleep. It ruins everything. It ruins everything. Don't like the hot, don't like the cold. Just nice in the middle. That's how I like it. Now, astrophysics. So Astro, who is this for? So IB has Astro. Astro would be good for AQA, the optional module. So I've done turning points that we can do a bit of Astro. This is one that was recommended to me in a comment. So happy to sort of get into that. As always, if you've got questions, you can drop them in the chat and I'll make sure to answer them, or at least do my best. I will say, because it's not core syllabus, that I may not be like 100% on like all of the nitty gritty details, especially when you get into some of the like telescope stuff. Luckily, there is a public resource sort of mini textbook available. So I think because it's available publicly, I should be okay sharing it. Would this apply to Edexcel space physics? Let's find out. I am going to quickly Google Edexcel. Because most people I have are doing the AQA, doing the physics. So Edexcel, A-level physics space. In fact, no, I'll do it in the Save My Exams. I won't share the Save My Exams because paywall, but let me just sort of check the stuff. Edexcel notes. Yeah, the Edexcel spec. Is it... Do you have mandatory Astro? It doesn't look like you... Oh, you do have mandatory Astro. You have mandatory space stuff. So maybe that would be a good place to start. I'll look, because I've got the overlap between you guys and the IB. So if I get... And then I've got the AQA in a side note. So the AQA is the one with the most details. So that's the one I think I'm going to leave to the end. I'm going to do the core stuff that's common to everything and then dip into that as required. Let me get the IB open. So IB Phys HL notes. So that way I'll have the Edexcel notes to cross-reference with the IB notes, and that way hopefully everyone should be covered. A lot of the stuff, as you can imagine, because at a certain point, physics is physics, a lot of the stuff is going to overlap. OCRA stuff. Looks like we're going to get another spec up, guys. Let's go. Because like F equals MA is just F equals MA. But you're right. When it comes to Astro, let's make sure we know what's up. So Edexcel OCRA stuff. Let me find that out. And let's just tutor a bunch of people simultaneously. So in a bunch of different boards. What's the worst that can happen? So, oh no, I didn't mean to do that. Guys, I'm pressing buttons. We know what happens when I press buttons. Bad things happens when I press buttons. So let me get the OCR up and running. Revision notes. And yeah, as always, let me know if there's like a particular part of these syllabuses that you guys like want to go over. Yeah, there's normally some niche stuff in Astro. I know. Can we be honest about the fact that Astro is like not fun? The core stuff is fun. Life cycle of stars, great fun. Cosmology, great fun. Specific things, not fun. Not fun. Like it's one of those things where it's fun in theory, but in practice, actually having to answer the questions, not fun. So this is the OCR. Let me see if I can get your Astro spacey things. Where's your Astro spacey? There you go. So I'm seeing, yeah, you've got the general planetary motion, gravitational stuff. You have stellar evolution. Yeah. Okay, I'll cover, okay. Astro is what you're doing at university. Ooh, but you find the questions odd. I think Astro is one of those ones that lends itself well to research, but not that well to exams. Because I definitely, like, there's a lot you can do with, like, data analysis. There's obviously so much of space unexplored. Like, it's really good for, like, just analyze the data, post your findings. But you're right, questions? Odd. Right, let's get into it. Don't like memorizing stuff. Yes, exactly. Understanding stuff is good. Understanding the story is good. Memorizing random nonsense is bad. I know, exams are exams. Okay, right. Let me Miro whiteboard this. Because I don't want to go crazy, and the only thing I can share is the super detailed AQA one. In fact, let's start with what, okay, hey, I'm in charge. I can start with what I find most fun. Why don't I start with life cycle of stars? Because that's I enjoy that. So I'm gonna kind of tell the story. The basic idea is you start as your cloud of gas and dust, mostly hydrogen. This thing has mass. Because this thing has mass, there is a gravitational pull towards the center of gravity in the middle of the cloud. Therefore, the cloud gets pulled together under its own gravity. The individual particles of gas and dust, we know that there's conservation of energy. The gravitational potential goes down, so that gets converted into the kinetic energy of the particles. That causes the particles to move faster, and therefore the cloud to get hotter. This carries on. It carries on condensing and heating up until it starts to glow. It starts to glow red hot. It starts to produce light. We'll go into detail about why in terms of the temperature and the types of wavelength produced, but that's the idea. It condenses due to gravity. It heats up. It starts to glow. This is a protostar. Eventually, gonna keep on the chat. Don't even understand 95% of the universe. Yep. Hello, bye, ma'am. How's it going? So we've got this idea. So it's condensed under its gravity. The GP has turned into the kinetic energy of the particles. It's got hot. What happens then is once you get hot enough and dense enough in the core, then you reach the conditions for fusion to begin. And once you get fusion, then you have an outward radiative pressure, which balances with the inward gravitational pressure. The forces are in equilibrium, and you have reached a steady state. And that is called your main sequence star. And that's a good place to chat on. Let's see what's happening in chat. Yeah, full agreement. Okay, so we've got some main sequence. Main sequence is when hydrogen is fusing into helium, right? Okay, so then what happens next is kind of dependent on the size. But it basically stays there for the entire life. Well, that's the main body of the life cycle of a star. And what's happening is really dependent on the size. So if you are a really, really big star, yes, you have more fuel available to you because you have more hydrogen, but your core is bigger, where you are burning the stuff, you are burning through it faster, and actually you live less long. So we expect smaller stars to be long lasting in main sequence. We expect big stars to not last as long in main sequence. And what happens then is at some point in the life cycle of any star, the hydrogen in the core begins to run out. So what you have happen next is starting to fuse helium into heavier elements. The details of this seem to matter ever so slightly syllabus to syllabus. So I'm going to give like a basic overview. Because again, what I'm really doing here is I'm saying, all right, we have an hour. If you had the exam tomorrow, what's like the core central stuff you must get? For any of the small detail, feel free to hit your books. Make sure you know everything you specifically need to know. But what happens is hydrogen starts to fuse, which produces even more outward pressure. Or actually, no. So that is one explanation. Another explanation is as the hydrogen starts to run out, the radiative pressure decreases, which means the gravitational pressure outweighs it. It collapses a bit more. It gets hotter still. And then you fuse the helium / the hydrogen. It gets hotter, so the hydrogen just outside the core starts to fuse. Either way, what starts happening is you get new fusion happening that wasn't happening before. Radiative pressure increases. And then this thing starts to expand. It expands and it cools into either red giant or red supergiant. So now we get into the part where it really depends on the size. So for stars roughly the size of the sun, we know that it's going to go down the red giant path, where it is fusing helium into like heavier elements. Once the helium runs out, then you got really nothing left to do. And so the fusion will stop. You'll get a planetary nebula. The core, so the outward radiative pressure again goes away. The gravitational pressure means the core kind of collapses. The outer layers are thrown off in a planetary nebula. And what's left behind is a hot white dwarf, which is only radiating due to its heat, which then slowly dissipates and it cools, goes through the color spectrum, and just dies. That's for stars roughly the size of the Earth. If you are much bigger than the Earth, so I think the transition is about 3 times the size of the Earth, although I could be wrong about that. I think it could be more. But if you're super big, you're going to go into red supergiant, where you're going to fuse, I think, through a different method. I think it was like a carbon, nitrogen, oxygen system that I'm not super knowledgeable about in this moment. But what's going to happen is you start fusing heavier elements sort of up to iron, and because it's just like super hot, super dense, and it can just go ballistic. Once you run out of things to fuse there, then the outward radiative pressure stops, the core collapses, but it collapses so quickly and so forcefully that it explodes then. So there's a huge force inwards pushing the core together, and the outward layers just explode out in a supernova. That happens very, very quickly. And what happens with that core that's been exploded is it is either turned into a neutron star, where basically all of the empty space in an atom is collapsed. All of the electrons have fused with all the protons, and it just becomes a bunch of neutrons. And that's about sort of from about 1.4 to 1.4 to 3 solar masses if the core is that heavy. And if you're above 3 solar masses, then you collapse into a black hole. And one thing I think is very interesting about, while we're here, talking about, wait, where are you? I'll move you over here so I can kind of keep up with what's happening. But the one thing I find really interesting is just how dense a neutron star is. So if we think about it, we've got our atom and we've got our nucleus. We know the diameter of a nucleus is approximately 10 to the minus 15 meters. We know that the diameter of an atom is approximately 10 to the minus 10. Because volume is 4/3 pi r cubed, in other words, that the volume is proportional to r cubed, in other words, that the volume is proportional to d cubed, because the scale factor here going from nucleus to entire atom is 10 to the 5, the volume ratio is 10 to the 15. So in other words, only the volume of the nucleus is the volume of the atom times 10 to the minus 15. Only 1 in 10 to the minus 15 of an atom is occupied by the nucleus. So it is so much empty space. And all of that collapses to form a neutron star, which I just find very, very interesting. Right. That's sort of the off the dome explanation. What I want to do at this point is just to check in with my syllabuses to make sure I haven't missed anything important here. So I'm going to check in. So that's the Excel. Hold on. Let me Astro and Cosmo. So Astro, okay, so Edexcel doesn't seem to have a huge life cycle of the star section. Stellar evolution seems to be big in the OCR. It is certainly there in the IB as well, and it's 100% there in the AQA. So let me see if there's any specific detail I now need to get into. With forgiveness, I'm not going to talk about the type 1a supernova and standard candles in AQA. Ooh. The Chandrasekhar, I have never heard of this limit before. Chandrasekhar limit. Interesting. The maximum mass of a stable white dwarf. Yeah, 1.4 times the solar masses. Once you get bigger than 1.4. So that 1.4 times the solar mass. And that's when a core. That is an Edexcel thing. I'm seeing it in the Edexcel syllabus, and I'd never heard of it before either. So let's say, yes, that is Edexcel. But basically, it's sort of saying, yes, you saw me earlier kind of roughly know the tipping point for when you're going to go down these different routes, right? So your 1.4 to 3 times solar mass gets you neutron star. Bigger than 3 solar masses gets you black hole. Less than 1.4, you're into the solar mass pathway. So it's really due to the size of the core. So we've got a lot of leeway. So it's by the way, that's not the entire mass of the star. That's just the mass of the core. So if you're at the size of the sun or thereabouts, then you're going to go down the normal red giant pathway. If your core is more than 1.4 times the solar mass, and therefore your total mass is much bigger than the solar mass, then you go down your red supergiant pathway. So that, I think, is the sort of core connecting idea here. I think some of the details about the different types of fusion are things you're going to want to dip into for your specific syllabus. Wow. I did not know he discovered that at 19. That is very impressive. People are prodigies. Teo, like, kudos to him. That's insane. Okay. But I think that's a good sort of overview of the life cycle of stars. Hertzsprung Russell diagrams, that I think I should be able to share because of the publicly accessible textbook. Because, Lord, you guys know my artistic ability and lack thereof. I'm not doing it. I'm not attempting to draw a passable Hertzsprung Russell diagram. Nope. Although I don't really like the one in this textbook. But it is publicly available, so let's bring it in. And I'll drop a link to this as well in the chatty description-y nonsense. Guys, I'm so good at YouTube. Right, so here I literally found this by Googling. It is super accessible. Right. Yeah, there it is. Okay, so Hertzsprung-Russell diagram. This is your Hertzsprung-Russell diagram. You could also consider this. Hertzsprung-Russell diagrams have, in fact, let me zoom in sufficiently that I can. No, it's not gonna. All right. So you've got absolute magnitude, which is to do with brightness. You've got the brightest stars at the top, the dimmest stars at the bottom, and we have surface temperature on the sliding scale here, where ironically the hottest are here and the coldest are here. That's because this is kind of arranged by wavelength. Actually, at this point, it might be worth considering what these different classifications are. So if instead of sharing this, but actually, does that? It does. Yes, I kind of hate the conventions here. It is because it's a logarithmic scale, so you can kind of consider it like pH, I suppose. Where if you think about it, pH it's a similar idea to pH, where pH is the measure of the concentration of hydrogen. So like the concentration of hydrogen would go against in the opposite direction of the pH, and so I think it's the same thing with absolute magnitude. But I agree. Do not enjoy. One thing that's worth discussing before, but what makes more sense is what's happening here on the bottom. So let's spend some time. Ooh, hello, you're new here. Can I please get to know what this is? Yeah, astrophysics, but it's beginner intermediate. Okay. So what I'm doing here is doing some online tutoring, kind of free for the internet, to do with A-level physics in the UK. So in the UK system, A-levels are what you would sit at the end of your high school years at around 18. So this is your A-level/IB. It's kind of your high school equivalent, right? So this is not going to be at the level that you would do in university. And kind of as I said before, because there are different exam boards, you're going to require different levels of detail for different things. So if you're not currently sitting in A-level, you're probably just here for general interest. And so you can this won't affect you. But yeah, that's kind of what I do. I do some live solves of exam papers to demonstrate exam technique. And I do sort of seminar stuff like this where I go through topics. People do have an A-level in a couple of days, which is why I'm sort of prioritizing this. And by the way, I'm planning on doing some paper 2 physics multiple choice questions because a lot of the mark schemes only give the answers and not the explanations. I think it's worth demonstrating how I would do that. It's good broad revision. I'm not sitting there writing down a bunch of words, so that'll be quite fun. Am I the goat? Not really. I mean, literally the entire time streaming, I'm like, guys, I don't know about stars. I'm just doing my best here. But while we are here, let's talk about why you're a first-year aeronautical engineering student. You know more than I do. Congratulations! Yeah, you are upskilled from me, probably. Aeronautical engineering. Actually, engineering is so much fun. I did material science as my degree, so it was kind of adjacent. I really should have stopped sharing for the whole of that, because when I'm just chatting to chat, I should make a note of that. But reason why I'm stopping there, let's dip into the Miro whiteboard, because I want to explain the Wien's displacement law, because it's now coming up in a couple of places, so it's worth discussing. So Wien's displacement law talks about the peak, so the intensity at different wavelengths, right, at different temperatures. So what we find is that hot things have a larger intensity at all wavelengths, and the peak wavelength happens at the peak wavelength is smaller for hotter things. Should I have done this with color? Yes, I should have, but I don't think I can do that with, so I'll just, that's hot, that's cold. So imagine I had drawn this one red, and imagine I had drawn this one blue. So what we find is that the wavelength at peak intensity tracks this kind of it's inversely proportional. So lambda peak is inversely proportional to temperature. In other words, lambda peak times temperature equals a constant, which is like 2 point something something. I don't know it. I don't really care. It's something you can look it up in a formula book. But what this means is, if you can see the peak wavelength of light by analyzing the light that's coming from a star, you can work out the surface temperature of the star. And vice versa, if you know the surface temperature of the star, you can work out the peak wavelength. And that, by the way, when I was talking about the protostar, is why that works. Thank you very much. Oh my god, I forgot chat's available to look things up. That is super handy. Thanks, team. Yeah, so it's 2.9 times 10 to the minus 3. And we can do some dimensional analysis and realize that it's going to be meters times Kelvin as your unit. Right, so what does this mean for the protostar? So I said as the gravitational potential energy is converted into the kinetic energy of the particles and the temperature goes up, what is that going to do to the peak wavelength? Well, as the temperature goes up, because they're inversely proportional, the peak wavelength will go down. You currently, and let's remind ourselves of the electromagnetic spectrum here for a bit, if we're going to talk about a sliding scale of wavelength here, if this is like, yeah, this will be low wavelength, this will be high wavelength. We know there's visible kind of in the middle, and as you get to higher wavelengths, that is sort of out towards the red end of the spectrum. So you've got visible light here. This is where you're going to find your IR. This is where you're going to find your UV. We can see as the wavelength goes down, and you right now are a normal human temperature, you are 37 degrees C, you are emitting a peak wavelength in the infrared region. That is why you show up on infrared cameras. That's why we can see you with our night vision goggles. As temperature goes up, we can see that the peak wavelength starts to decrease. If it decreases sufficiently, we can see it enters that visible spectrum at the red end. That's when things start to glow red hot, when the peak wavelength is now in the visible spectrum. As the temperature increases further, the peak wavelength will decrease further, and you'll start to move through. It will glow red hot, then orange, then yellow, and then blue. And that explains why things glow. That explains why we can see stars. It also explains, if I go back to the, it also explains how this works, right? So this is a measure of surface temperature. Kind of, you're like, hang on a minute, why is it small, like large going to small? Because you can almost imagine instead it's measuring peak wavelength, right? Because that's the kind of equivalent measure, and that is increasing from functionally 0 up to like a lot. I say that, you can run the numbers on that. But that's what's happening. It's increasing peak wavelength because of decreasing surface temperature. So what we find is these main sequence stars happen kind of in the middle. You have this kind of S shape. I think if you want to remember the shape of a Hertzsprung-Russell diagram, think of it like a percentage sign. Where you have your white dwarfs down here that are on their way out. You have your red giants here that are kind of dying. You have all of these stars that are slowly moving through from main sequence to red giants because, and we're saying this pre-main sequence, so these are your stars. That's what I was saying. So these are your protostars before you start actually sort of fusing and emitting light. So up here, absolute magnitude is to do with the brightness. It's to do with the kind of the power output of the star. And this is to do with, and that will come sort of from, does the transition from red giant to white dwarf happen almost instantaneously? Well, we know certainly that the transition from red supergiant to neutron star would happen very, very quickly because that happens, that's kaboom, that's supernova. That's a very good point about over what length of time. I would not expect planetary nebula to happen as instantaneously as supernova. Could be wrong, but again, I'm really talking at the level of like year 12, year 13 anyway. So let me actually, that's a good point. Let's see, red giant, planetary nebula. I think it would happen quickly. I think it happens very quickly, but it takes a very long time for that sort of nebulous cloud to die away. By the way, lifetimes of stars, while we're here, this is sort of explaining what I was saying earlier about the fact that the bigger masses do not live as long because they burn through their stuff a lot more quickly. super dense, blah, 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 blah. Yeah. I mean, I'm not going to sit here and read an entire textbook. No one wants to see that. That's boring. It's publicly accessible, and it has a lot of detail. So, by the way, if you want some further clarity on anything I'm saying, I'll drop that as a resource. And you can kind of look it up sort of in your own time, especially because we're like half an hour in and I've still only talked about life cycle of stars. But right, Wien's displacement law, check, discussed. I think that's very important. Energy released in fusion reactions, that's kind of stuff we talked about before when it comes to binding energy being released. As you start to fuse elements, the binding energy per nucleus increases massively, and so you get a large release of energy. Is there anything else I want to say about stars? If you got questions about stars, within reason, drop them in the chat. Because there are some people who are like really knowledgeable about astro, and I am. Again, you just like drinking game, count the number of times I'm going to say that. I'm not the one, but I can kind of do it for, GCSE and A level, and that's all that counts. So what else do we need to consider here? I'm happy to move off from that because I especially want to make sure. Well, okay, let's talk about. No, are standard candles coming up enough? I think standard candles are coming up enough. Parallax is coming up in a few syllabuses, so it's maybe worth discussing that. Yeah, okay. So let's discuss parallax. So the idea behind parallax, in fact, if I've got the resource, I may as well use the resource. Because again, that was a pretty nebula. So let me see if they have a good explanation for parallax, which I think they will. That said, I can't see it. So I'm just going to go back to the mirror whiteboard and we're going to discuss what parallax is. So parallax, you think about it. Actually, let's start by grounding you in your real world understanding here. You know, if you're moving in a train, that the stuff closest to you is moving super quickly and the stuff further away from you is moving super slowly. And that's kind of a similar idea to what's happening with parallax. So if I have a star sitting out there in space, and I'm just a lowly person on Earth, orbiting my little sun. No, too much. So I'm orbiting the sun. That sun, this is the Earth, and let's say we've got a star out here. We're going to consider two separate stars, right? We can see over a 6-month period, we are now on the other side of the sun. And so we are approaching these stars from a different angle. And because we are seeing them from a different angle, we know the ones that are like the backdrop stars that are super far away, they're just not moving. They are not moving. But the ones who are closest by are going to shift relative to the backdrop. So if we have a star here, we're kind of looking at it from this direction in January, and we're looking at it from this direction in July. And so we can see it's going to shift against the backdrop. And what we see is that the bigger the shift is, the closer to us the star is. And by measuring that shift, we know exactly how close it is. You always miss the 6-month marking point in questions. Yeah, it's super important. Because what you find, I can't remember the exact, but what we find is, so this distance here from the sun to the Earth is 1 astronomical unit. And this is obviously a very small angle. So tan theta is approximately sine theta is, so theta becomes approximately equal to this distance, 1 astronomical unit, all over the distance of the star to the sun, which is about the same as the star to us over the distances that we're talking about. And there's a simple definition, which I can never remember, so I'm going to get the IB formula book because it's going to tell me. So this is to do with what a parsec is. So I think it's when the angle, the parallax angle is 1 arc second. from memory. Let me just confirm that I'm correct about that. For physics. Also in chat, if you beat me, then feel free for the exact definition there. Where's my annotated physics from the book? Is it there? No. Yeah, 1/3000th of a second? Yeah. So let me get this precisely, guys. I want to make sure you're completely informed about this. So solar parallax. Okay. So we know that tan theta is exactly equal to this astronomical unit, and when that distance is 1 parsec, then the angle is 1 arc second. So what does that mean? Well, what you kind of do is you split up 1 radian. Let's talk about what this means. So let's say we've got an angle of 1 radian. So we're kind of breaking it down now. So we're dividing 1 radian into 60. Well, that would be 1 arc minute. And then you can further subdivide those arc minutes into arc seconds. And so 1/3600 is 1 arc second. And when that angle is the parallax angle, we define that distance as being 1 parsec away. So by measuring the parallax angle, by seeing how much it moves over a 6-month period, we can get the parallax angle. From getting the parallax angle, we can tell how far away it is using this formula. So that's the basic idea. Again, for more detail, you can get sort of deeper into that. Would it be the distance from the Earth to the Sun that is subtended by an angle of 1 arc second? So the arc second, I think it's the angle as I've defined it here. So if I kind of zoom in a little bit, it's this here. So it's the one kind of halfway in between. So it might make more sense if I kind of just get rid of that line entirely. It's that perpendicular distance from the sun to the star as one of your legs, and then the 1 astronomical unit as the sort of smaller end of that right triangle there. That's how everything is defined up. Oh, should I talk about emission and absorption spectra? Let's not right now, just because we're already sufficient way in that I really want to start getting into the cosmology, like the core of that. Yes. That would be star to Earth. But if remember, over the distances that we're talking about, that angle is so small. If you think about what that is in degrees, it's just like basically nothing. And so you're very, very much into the region where small angle applies. The distance from the star to the Earth is functionally going to be the same as the distance from the star to the sun. So they're kind of the same thing. All right. Now, let's get into some brief cosmology stuff. Where is, I feel like in the IB, it should be, I thought they had more than that, you know. Unless I'm drastically misinterpreting or misremembering. Oh, it was in Doppler effect. Okay, they kind of scatter their astro around. But let's talk about the cosmology stuff. So the basic idea behind the cosmology, first of all, what is cosmology? Cosmology is the sort of study of the foundation, the starting point of the universe, right? So it's big. So Astro is kind of big. Cosmology, yeah, that's kind of how I think about it. It's to do with the origins of the universe. Now, we collected a bunch of evidence which has slowly informed our understanding of how the universe came into being. A lot of that stuff is the stuff that you got to get examined about. So some of the classic ones that you'll know now are the cosmic microwave background radiation and galactic redshift. Those are your big two. What I'm going to do now is kind of go through and see what I can find from different syllabuses that are the most important things to discover, including use of the Hubble constant to estimate the age of the universe. So what do we know? First thing we know, let's talk about galactic redshift, because that I can just wax lyrical about. So what we know from the Doppler effect, 1/h, exactly. What we know from the Doppler effect, if an object is moving away from us, and let's get into the nitty gritty of this explanation while we're here, by the way, because this can help you in waves. When an object is moving away from us, the wave fronts become further spaced out because the object is moving away at successive moments in time when the wave fronts are created. So it's the wavelength plus that distance moved in the time period. So you get that kind of increase. The waves spread out, which means the apparent wavelength increases. And because the speed is the same and v equals f lambda, that means the frequency appears to decrease. So as an object is moving away, we get a decrease in the frequency of the light and we get an increase in the wavelength of the light. Now, an increase in the wavelength of the light means it's shifted towards the red end of the spectrum. Because we know that stars are mostly made up of hydrogen, and because we know that hydrogen has very specific, in fact, now I will get into this. Because we know that hydrogen has very specific transitions due to its energy levels. So we know n equals 1 is like way down at the bottom, but then we got n equals 2, 3, 4, etc. We know that you can get emission when an electron de-excites energy levels. That emits a photon. We know we get absorption when an electron is excited up energy levels. The emission spectrum, in my opinion, is just, I mean, they're complementary, right? You basically, it's one minus the other. So in an absorption spectrum, you're going to get broad spectrum, and then you're going to get a few lines that are removed because those are the ones that get absorbed. In an emission spectrum, you're going to have nothing. It's going to be purely dark. And then you're going to get a few sharp lines at specific wavelengths where emission can happen. And we see those wavelengths appear. And because those wavelengths are emitted by transitions between energy levels, and the energy of the photon emitted is exactly equal to the energy difference between the energy levels, the energies of the photons emitted are very particular to the electron structure of your element, which means that every element has a unique fingerprint of photons that it emits. So if you look at an emission spectrum, you know with certainty what elements are present, which is how we know that stars are mostly made up of hydrogen with a bit of helium. By the way, while we're here, I think is it the Fulmar, the Palmer? It's got a name. But in anything in the visible spectrum, when we're talking about hydrogen, that is specifically transitions involving n equals 2 from above. These transitions down to n equals 1 are too high energy. They are in the UV and beyond, and they will not show up in your visible spectrum. So for hydrogen, we're talking specifically about n equals 2. So these different transitions to n equals 2 will result in photons being emitted. So we know the exact fingerprint I can't remember what it is off the top of my head, but we have these specific emissions that happen. We know with certainty what we expect to see for hydrogen. What we can then do is to measure the apparent wavelength of the, so if all of those are just shifted by a tiny amount, we know, hey, the thing we're looking at is a star, it is hydrogen, and these are shifted by a little bit. And if we can measure that redshift by using the equations of the Doppler effect, we know exactly, with certainty, how fast it is moving, and that it is moving away from us. What we find is that the farther away a galaxy is, well, first of all, almost all galaxies are moving away from us. And the further away a galaxy is, the faster it is moving. So what that means is not only is that galaxy getting away from us, it's also outpacing any galaxy in between us, so it's getting away from them as well. In other words, every galaxy is moving away from every other galaxy, and the entire universe is expanding. And we can tell all of that. Balmer lines, thank you very much. Or is it Palmer lines? Something like that. Now, so what we can tell all of that just by looking at the emission spectra of stars from distant galaxies. So we can tell, and by the way, if you want to know the distance, how do we know the distance? I think that's to do with standard candles. Is it worth talking about standard candles? Yeah, it's worth talking about standard candles. Let's do that. Why not? So the way a standard candle works is we have said, remember, there's the transition, right? There's that transition. If your core is 1.4 solar masses, that is the transition point between Earth, Sun-like evolution, where you go down the red giant planetary nebula route, or the supergiant supernova route. So the idea here is when you have a binary star system and one of them is kind of dying, we know it turns into a red giant. Well, so let's say we got it two binary. Okay, let's still do, I'll go to the whiteboard when I need to. So we got these two stars. They are kind of orbiting each other. It's a binary system. No, I think let's get this. I want you to see it. So, because I think I remember this is one of the ones where it is actually quite good, this diagram. Have I overshot the mark? Have I undershot the mark? Where did I think I missed entirely. What's happening? Sorry, I got lost. Take two. So page 50. And that's page 2. Okay. So yeah, I want to go to around like sort of page 53 or so. Apologies for the transition, but it will be worth it. Oh, maybe. Oh, I thought I would see a better diagram. Oh, well, never mind. Okay, so the basic idea, you've got these two stars orbiting each other anyway. So they're both kind of dying. They got there around the same time. They're both dying. One of them has already turned into a white dwarf. And the one nearby is still dying and it's turning into its red giant phase. So a lot of its stuff is expanding out and it's starting to get a little bit closer to that white dwarf. And so what the white dwarf starts doing is it starts sucking in some of the outer layers of the nearby red giant. So the red giant is now slowly feeding this white dwarf, which is gaining mass, gaining mass, gaining mass. And as we saw, that leads to there being an unstable sort of critical mass, right? When you get to 1.4 times the solar mass, kaboom. And so that is what happens. You get a star that was not ready to go supernova with a nearby star that starts slowly feeding it until at just the right transition point, it goes kaboom. Because that happens at just the right transition point, we know that they have it like sort of exactly the same behavior, right? They explode, they have kind of the same mass, they have the same magnitude, they behave in very, very predictable ways because they happen at that transition. So whenever we see that type 1a supernova, we call it a standard candle because we know exactly what's happening out there. We know exactly what its true brightness is. And then by looking at its apparent magnitudes, we can get a sense of how far away it is. And that, I think, is how we do distances, long distances. So this parallax angle that we discussed is really good for getting a sense of nearby stars, because those are the ones that actually shift over a 6-month period. But if you are too far away and you don't really shift, we have to use the standard candles to get a sense of where you are over cosmological distances. So that's kind of how we know how far things are that are really, really, really far away. And that's how we know that the further away a galaxy is, the more redshifted it is, the fact that everything is expanding away from everything else. So then, so that's your kind of galactic redshift stuff. Am I missing cosmology? I should have binary stars. Let me see if we got anything interesting here. Is that interesting? Not really. So yeah, galactic redshift kind of tells us about that. Hey, just joined the streamed. As the title looked interesting. What's going on here? Hello. You are the second random person to just jump up on today. What's happening here is I am a tutor. I live stream tutoring to the internet for free. We are in the middle of exam season. So here in the UK, we have A levels. IBs have just finished, but a lot of people have an A level in like a couple days. So we're talking about the exams you sit when you're 18, end of your high school. And I'm just kind of going through it for that. So this is not sort of like this is sort of like a super complicated like physics, like university level physics. This is really just preparing for specific syllabus points. And I kind of do it like, if you had an exam tomorrow, what are the really important core points that you would need to know in order to do decently, right? Now, because this has multiple different exam boards, some of the details vary, but I'm kind of just covering the core basics, which are sort of stellar evolution, which is a core that happens across all of them, and cosmology, that kind of also happens across all of them. So I've now talked about stellar evolution, I've talked about galactic redshift and the evidence for the expanding universe. And while we're here, actually, let's talk now about Hubble's law. So we said that the further away an object is, or a galaxy is, the faster it's moving. So we can draw a graph. Well, in fact, why am I? Yeah, so the distance against the redshift. So if we draw redshift on the y-axis, if that's your redshift, and this is your distance, then what we get is it's directly proportional straight line through the origin. The gradient of that is the Hubble constant. Okay. So it's directly proportional. You get your Hubble's constant from that. And what this also means is that we get not the redshift, but if we convert the redshift into speed, we get that the speed of a recessing galaxy is equal to Hubble's constant times its distance. By the way, now that we've got this as our starting point, so what does that mean? It means that all of the galaxies are moving not just away from us, but moving away from everything else as well. And so the basic idea behind the Big Bang is, all right, for all galaxies, if we look forward in time, we know that everything is moving away from each other. What if we reverse the arrow of time? What if we move backwards? Earlier in time, they must have been closer together. Earlier still in time, they must have been moving closer together. Moving earlier still, and they kind of track back, and you think, all right, we must have started at one point in space. Because does that make sense? Not really, because it's not that things are The Big Bang is what created the concept of space itself. Kind of complicated, but basically what we can do is we can reverse engineer it and think, how long have we already been expanding, right? What's the proof for this? I can't quite remember. No, I can. So, I mean, at a very simple level, if we think that something is moving with this speed, the speed depends on the distance. We know that speed is equal to distance over time. So we know that time is equal to distance over speed, which is equal to 1 over h. So by measuring 1 over h, we can get an estimate for the approximate age of the universe, which is your 13.8 billion years. Oh, I lie. It's 14.5 billion years. Another great piece of evidence is the cosmic or cosmological microwave background radiation, the CMBR. There's a really cool backstory behind this, which is they created their radio telescope. They were trying to measure something. They pointed it at a blank part of the sky just to calibrate it, make sure it was working. It was like, hang on a minute, why am I getting a huge amount of signal? And they moved it around and went, why am I getting a huge amount of signal? And then went, God damn it, I'm sure I've built this telescope wrong. And then kind of went, what if I didn't though? What if that is accurate? What if that actually is this radio signal that is just everywhere, or this microwave signal that's everywhere in the universe? And then won a Nobel Prize, I think. I might be getting that wrong. Oh well. But the idea behind that is that is evidence. If you think about an explosion creates some light. The Big Bang, the way you can think about it instead is, as we saw, everything that has temperature radiates heat, and you can measure that peak wavelength, right? By getting the peak wavelength, we know the temperature. And so by getting that peak wavelength of the CMBR, we can estimate the temperature of the universe, which corresponds to a black body, from looking at a textbook, of about 2.7 Kelvin. But the basic idea behind that is that would have been extraordinarily high energy gamma radiation at the Big Bang, and it has slowly expanded over time as the wavelength gets longer and longer. Okay. So those are your two core ideas there. Am I going to go? Let me just, again, I'm going to do a syllabus sweep and just see if there's anything else we need to know. CMBR, I don't think is in there. Oh, there was a really cool one. Someone brought it up in a stream. And it was to do with predicting what's going to happen. Is it going to be big crunch or big freeze? And it has to do with, yes, there's a tipping point, which is dependent on the density of the universe. All right, track this through with me. So as we said right at the start, the very first thing we said was about the evolution of stars. You start off with a cloud of dust and gas, which then starts to collapse into its center of mass in the middle. The force of gravity pulls it in. By that logic, the entire universe should have a center of mass somewhere in the middle, and everything should be feeling or experiencing a force of attraction towards that center of mass. Now, if that force will depend on the mass of the universe, but more importantly, and the derivation escapes me in this moment, but it does. The idea is that it depends on the density of the universe. So there's the total mass that exists in the universe, and the total size that the universe now is. If the density is above a critical density, a tipping point density, then there will be a net force of attraction to inwards that will be sufficient to get the universe to stop expanding and to start moving back together again, which will cause a big crunch. If instead the density of the universe is below that critical value, the force of attraction will not be sufficient, and it will expand infinitely in a sort of big freeze. And if the universe happens to be exactly on this critical density, then it should at some point stop and become static, which would be weird and cool. And none of us will be around to see it. That's kind of off the top of my head. I can't remember which syllabus that's in, but if that's relevant to you, this is your reminder to go look that up. Look up how to derive. In fact, was it? I'm going to have a quick scan again in this textbook to see if it is in here. Quasars, exoplanets, no. Density of the universe, no, it's not in here. Okay, so I'm gonna. It sounds like it is sick. I remember actually it was one of the things in Astro I quite liked, and I think it was out only quite recently. Someone got me to explain it. I'm gonna quickly check equations for cosmology in the EdXL syllabus. We have the Hubble equation. Been through that. And then cosmology, what are they talking about? Again, the Hubble constant, that's the basic idea. Galactic redshift, it's huge. I'm seeing dark matter happening in some syllabuses, so we can maybe talk about that. The basic idea is that things don't behave the way they should based on the mass we can observe. What explains it is the fact that there's some mass that's unaccounted for, and that is dark matter. I think part of that is, for instance, I think it was spiral galaxies. We know that in fact, we can tie in your circular motion here. F equals mv squared over r. So it's somewhat the centripetal force, obviously. So there are relationships here, right? The force of gravity is providing that centripetal force. We know how fast things should rotate depending on their mass, which provides the force of gravity. And what we find is that based on the rotation of spiral galaxies, they rotate faster than they should, I believe, based on the mass we can observe, which is only explainable if they have more mass than we can see. So I think that is evidence for dark matter. But hold on, in the EdXL syllabus, we're seeing we would expect the velocity of an object within a galaxy to decrease as it moves away from the galaxy's center because of weakening gravitational field strength. So it's not concentrated in the center, it's spread out. But the observable mass is concentrated in the center of the galaxy. Okay, basic idea is there's lots of physical things that we observe that can only be explained by mass being there that we cannot see. Remember, we can only see it if it's emitting light. So dark matter is stuff that we cannot see, but that exists out there. Is there anything else for the EdXL? No. Cosmology, there seems to be a lot of stuff here in the OCR. Let's look at the expanding universe. I think this is going to be galactic redshift again. Yes, it is. Big Bang, age of the universe we discussed is one over the Hubble. Good. Evolution of the universe. Oh, you've got a nice detailed one. Okay. Oh, but that was early universe. Your dark energy and dark matter. Yeah, that's all the same. So dark energy is the type of energy that permeates the whole universe and opposes the gravitational attraction that should pull things back together again. Because what we find is that the universe is not just expanding, it's accelerating. And we're like, wait, what? Shouldn't gravity be pulling it back in? And so dark energy is kind of just what we use to explain that. Someone says, I've heard that after the Big Bang thing, universe never stopped growing, so it will never end. Will it collapse? Yeah, no, Earth is going to be Earth is going to get done when the sun gets done, because the sun's going to turn into a red giant, which I don't think it's going to expand far enough to swallow the Earth, but it's certainly going to just like life will not exist on Earth when that happens. Yeah, we'll be long gone. Oh, one last thing that's kind of interesting. So the one thing I really like about Astro, it's one of my favorite things, is we know from the binding energy per nucleon curve that fusion is only really viable up until iron 56. For elements to exist past iron 56, we need to smash them together in a way that isn't favorable, and the only thing that is powerful enough in the universe to do that is a supernova. The fact that we on Earth have elements that exist beyond iron is evidence that our solar system was created from the remnants of a supernova. So the universe started, we're like 10 billion years into the game, supernova happens. Oh no, Earth gets created at 4 billion years. I don't know when the sun was created, but basically, there was an entire huge star that already existed. It went supernova. It had time to like live, die, explode, and for the sun to get reformed from the remnants of the supernova and then create the Earth 4 billion years ago, and now here we are. That I like. The fact that and I'm really curious about whether because I don't know this off the top of my head either, but whether elements that exist past iron are essential to life. And if they are, then life would only be possible in the remnants of a supernova, which is just really cool. So that's fun. Here, again, I'm not seeing that much in the IB. Cosmology, evidence for the Big Bang. Yeah, so I think that covers everything I want from cosmology. Classification of stars. I'll let you get more into the nitty gritty about like the absolute magnitude equation work, because there's specific equation work that happens in the AQA that you should really get into. If you're in AQA, by the way, I haven't gone at all into telescopes and things like chromatic aberration, spherical aberration, all the different the way that we can extract information from all the different parts of the electromagnetic spectrum. That's all stuff you should look into a bit further. Are you going to go through telescopes detecting stars? I can do if you want me to. I mean, I got time. Are you AQA? If you are AQA, then I can spend a little bit of time going through telescopes, if that's helpful. I will also add that things like that is stuff that I do not teach for your AQA. All right, we can spend some time. For everyone else, you feel free to go because we're going to get into some AQA specific stuff. When it comes to the telescopes, you should bear in mind, just for sort of, full disclosure, I haven't taught this in a while. Wait, I lie. I've never taught this ever. And so we're going to I did have to learn it like way back in the day, but the specifics of it, okay, I'll check, drop in the chat if you have access to the textbook that I've been sharing, because it's free online. You can use that to sort of fill in any of the gaps that I'm missing here. I'm going to highlight the core ideas. But also, rather than me just sort of blindly go through stuff, even if you know it, if there's something specific in telescopes you want me to go through, feel free to drop that in chat as well, and I can kind of dip into that specific thing. If I share the screen, yeah, you've got your own book that goes through it. So sharing this one that, again, is free and available online. These are all the subtopics that I see within telescopes. And so we can go through any of these that you kind of think you need to go through. I think from my perspective, some of the important ones here are chromatic and spherical aberration. I would expect resolving power is a huge one. And collecting power, the way that different telescopes work, an individual telescope versus when you have different telescopes working together. Those are some of the things that I would really expect to come up if I was writing a paper on this. So again, rather than go through all 20 pages of this, if you've got something specific you want to go through, please let me know. Chromatic and spherical aberration and resolving collecting power. Perfect. Okay, so chromatic and spherical aberration. The idea here, if I go to page 5 of this document, chromatic and spherical aberration, one thing we know, if we're talking, in fact, no, let's rely on me for a bit. What we know is that if we're talking about optical lenses, it is about collecting light at a focal point. Lies. So many lies. This involves, close enough, refraction, right? This is done by the process of refraction. And as you know from your optics section of your syllabus, you know that the refractive index is not constant for all wavelengths. The refractive index is different for different wavelengths, which is why you're able to get dispersion through a glass block. The refractive index for red light is smaller than the refractive index for violet light, so red light is less deflected than violet light would be, or than blue light would be. So what this means is not all the wavelengths are affected the same way by the lens, and so not all the wavelengths would be expected to have the same focal point, and this leads to a smearing of color. That's chromatic aberration. So showing you the diagram here in the book, chromatic aberration is here where the red light is bent less than the blue light, so they have different focal lengths, and so they kind of focus in different spots, and this causes so that's chromatic aberration, which prevents you from getting a nice clean pinpoint image. They have a demonstration here where we can see it's sort of blue in and it's red on the outside. You can also get spherical aberration if the lens is not perfect, which causes the light to not be concentrated in one fixed focal point, which is kind of like how I demonstrated on that diagram there, where I kind of just missed the mark, right? So not all the beams of light that arrive parallel from and by the way, parallel beams of light means source is infinitely far away. In other words, light from a star. So would not be concentrated on one focus and would lead to a blurry image. So that is chromatic aberration versus spherical aberration. There is this setup here that can help you with chromatic aberration, going through a double lens to sort of have it work both ways to sort of undo that effect. We have these reflecting telescopes, which can also experience some spherical aberration if they do not reflect all the beams onto the same focus. There's some specific stuff I think matters less. That's the core idea. Let me also go through, you said resolving power. I think that matters. So the resolving power, this has to do with how close two things can be and still be resolved as distinct things when viewed through a telescope. So we know if they get too close together, the images would smear together and we would observe them as one image. So they have to be sufficiently far apart to be distinguished. And the resolving power is about how good your telescope is at distinguishing two nearby images. So this is your classic. The one on the left, that's two distinct things. This one here, this one on the right is certainly, it appears as one image, even though they are technically far apart. So what you get, the reason why this happens is because you get this airy disk, which is basically due to single slit diffraction through a spherical aperture. So we know from single slit diffraction, we would get a central, just remind you about single slit diffraction for a minute. So single slit diffraction, you would get and this is through a one-dimensional slit, you would get sort of little fringes, then one big central maximum, and like little. So the idea is if we had that in one dimension, but we sort of rotated it circle, it means you would get like a circle, a bright circle in the middle, and like sort of light fringes on the outside, right? So that's how that would be kind of observed if we took that central peak and sort of rotated it almost like a volumes of revolution through 360 degrees. So single slit diffraction, tying that in cross syllabus when I can. If we go back here, that means we get, when something is moved through a single slit, which your aperture is, it means that one object has this single slit diffraction pattern. The Rayleigh criterion states that you are able to resolve two nearby things when the maximum of the first object coincides with the first minimum of the second object. So if we had another object here with its first maximum here at this first 0 point, that is the limit at which they could be observed. So if that happened there, so this is the one on the left is our first object with its sort of peak here. If this peak coincides with this first minimum, then they can be resolved. All right, so that's the core theory. You can apply your single slit diffraction understanding to work out where that is based on the fringe separation. And then we can apply that to work out the resolving power. So that's kind of showing the sort of where the understanding is going to come from for this. So what we say is this first dark fringe is given by the formula sine theta equals lambda over d, where d is the diameter of the lens. So that's kind of the aperture through which the diffraction is happening. So small angle approximation, we say that theta is approximately lambda over d, where theta would be the resolving angle. So if we know our aperture diameter, and we know the wavelength of light we're using, we can work out the angle that can be separated. That theta is the resolving power. So here it's not quite showing it as I would like it, but do they now have Rayleigh criterion? Yeah, here we go. 2-point objects can be resolved if their angular separation is at least lambda over d, which is when the first maximum coincides with the first minimum of the other. So this is the minimum angular resolution. So in other words, if we know our d and we know our lambda, we can work out the angular separation of two objects that we can resolve, which makes a difference because as we saw with parallax, that sort of, sorry, that thought just ran away. So this lambda theta equals lambda over d is going to tell us the angular separation of two objects that can just be resolved, which then tells us, if you know how far away they are, how separated they have to be in order to be resolved by our telescope. So here, this is d, this is wavelength. We can work out what lambda is. So we know the minimum angular resolution. What's the smallest detail of the telescope that you can detect on the moon? Well, what you would do is you would set that angle. And we know the distance to the moon, which means we can just set up a right triangle, right? So we know the angle, and so we can set up tan theta, or rather just, which is approximately equal to theta. So we would say theta is just equal to the distance. Let me show you what I mean. So here, once we've worked out that theta is equal to lambda over d for the resolving power, we can also say that is the angle that two objects separated by a distance x can be resolved. If we know that this distance, I'll call it L because d is taken. If we know the distance to that object, we can work out x because it will also be x over L. So in other words, x is equal to the resolving angle times the distance to the object. So as in the case here, if I go back to the textbook, then in this case, once we've worked out the angle from part A, we can use that angle, we can multiply it by this distance to the moon, and that would get us the distance of things on the moon that can be resolved by our telescope. So that's kind of how to use these in application, right? And then collecting power is proportional to the aperture squared. Is there anything relevant there? Not really. So that's not a huge thing. But I will say, I think there might be something to do with sort of like telescope arrays to maximize. So we basically see that the resolving power increases the bigger d gets. So you want your aperture to be as big as humanly possible in order to improve your resolution. Because if you have a bigger d, then you have a smaller resolving angle, which means you can see two things that are closer together than they would be otherwise. So you can just pick up more detail in whatever it is you're looking at. So aperture size is big. Big aperture size is good, but as we saw, that can cause problems with our spherical aberration, with our chromatic aberration. That can cause problems just in the terms of the physical engineering of crafting lenses or reflectors that would be able to resolve that well enough, right? So your resolving power in theory is no good if in practice it doesn't resolve onto a fixed point, right? So those calculations assume perfect lens action. Let me see if I've got... so I want to do, just a little bit of work on, so that's resolving power. Radio telescopes, infrared. I'll let you go into detail on those, but I really want to talk about using producing large diameter telescopes. Again, that is an issue, and again, so that you want to go into. This is the one I want to discuss. So, no, that's a very specific example. I think in terms of core detail, everything I've been through is okay. Let me know if you want to go through anything else in there, but hopefully I think that kind of covers everything you need to know about the core essentials. The most important stuff is the stuff you can do calculations with. Any of the specific detail you can kind of just pick up as you go, but I think the most important stuff is that stuff. It's the Rayleigh criterion, it's the theta equals lambda over d, resolving power, how to apply your resolving power, and what that means for the production of telescopes that can kind of handle those requirements. So with that, hopefully you find that okay. I think I'm going to pause there. I'm going to give it a bit of a wind down time in case there's stuff you want to pop in chat for me to go over that I can react to. What I will say is I'm planning on going live. I think I'll throw one in tomorrow to go through some of the multiple choice stuff. I think I'll do that for AQA because it's the most common board. I might scan some OCR papers or some other papers to see if there's any multiple choice for me to go through. Hope you guys found that useful. And in the absence of seeing anything in chat, I think we're going to wrap up and you can go watch a football match that apparently is happening that I'm sure we all care about. Yeah, you got a couple days left. It's on Monday. Final few days. Hope you guys are finding the prep okay. Keep calm, carry on, keep doing what you're doing. And I will see you tomorrow for some multiple choice. And if not, I'll see you after the physics. Oh, you left a request. I'm so sorry. Apologies. Could you go over the differences in the setups for radio and regular telescopes? That I can have a look at. So radio telescopes. Let me see. Okay, so a radio telescope. Let's have a little look. So radio telescopes from the side of things. It seems to be reflecting onto a parabolic dish. We have our resolving power, as you know. Now, we know that the wavelength is very long for radio waves, so it means that the resolving power is not great if you use a single thing. They can operate in the day as well as the night because obviously, that's fine, blah, 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 stuff happens. But main issue is to do with the fact that wavelength is so big. Means that what we can do is to combine the signal from two radioscopes in a radio interferometer. And we get an interference pattern. So the baseline between the antennas is made very large. The image resolution can be hugely improved. That's basically what you do there. So you can separate them out. And that allows you to kind of get a much bigger resolving power. So instead of becoming lambda over d, it becomes sort of like a lambda over L situation. So first of all, yes, that the fact that they reflect onto a point, whereas optical telescopes are much more to do with like lenses. So you're not reflecting the light with optical, you're going to be using a lens setup, which looks like this, where light comes in from infinity at a bit of an off-axis angle, and then you use a converging lens to converge it onto a single image, which is then looked at through another lens, which makes the light look like it's coming from infinity, and you would view it on this side. So you would see the light coming from infinity, but you would see it magnified. So it's to do with lens action, where you can calculate as well the magnification based on the focal lengths of the lenses used. So in terms of functional application, it's lens action for optical versus refracting parabolic dish for radio. And in terms of the resolving power, lambda over d, optical is fine, but for radio, the wavelength is big enough that it means it's not great resolving power, and we typically use different telescopes placed at a difference apart to create a much bigger effective aperture to much better increase that angular resolution. So hopefully that makes sense. And in the meantime, I already kind of did a bit of a wind down. I suppose I could do a bit more of a wind down because I always need to give enough space and time in case you want me to go through something else. That helps. You are very welcome. I will say it reminds me of one of the best teaching jobs I've ever done. Is a guy texted me at 11 p.m. the day before a chemistry exam, and I was like, "Oh, I don't really do chemistry." And he's like, "God, this is an emergency. Please help." So I got on, and not only was it chemistry, it was medical chemistry, kind of an optional module like this is. And he sent me an online textbook kind of like this. And in an hour and 20 minutes, I read the entire thing, synthesized it, gave him the most important points, and he got a 7, which is the highest you can get in IB. Wild stuff. Best teaching of my entire life. Right, I'm going to give myself some voice rest. Hopefully that makes sense. I will see you guys on the flip side. By the flip side, I mean tomorrow for some multiple choice work. In the meantime, work really hard. See you then. Thank you very much, guys. Thanks for popping in. Take care. See you next time. Bye-bye.